Hello everyone, I am Samiha. I am going to present our paper Leveraging Code to Test Co-Evaluation Patterns for Automated Test Case Recommendation. My co-author is Dr. Muna Rahimi. So what is this work all about? We all know that software systems change continuously. So evolution is an innate process associated with modern software systems. So when the source code of some application is modified, what happened next? The corresponding test code also needs to be updated. And manually propagating these changes to the test code is a tedious and costly operation. So there are some existing tools that generate the whole test suite, like EvoSuite, Randup, Editor 1. But as demonstrated by some studies, these tools lack real-life applicability. So having that problem in mind, in this paper, we proposed a prototype tool, Test Source Evolver, TSE, that kind of complements the existing automated test generation tools. TSE helps the test automation process by providing useful test cases, either during the development phase or the maintenance phase of a software application. This paper is based on our previous paper, Patterns of Code to Test Co-Evaluation for Automated Test Suite Maintenance. In this work, we have documented 4 major co-evaluation patterns between source code and test code. And in the current paper, what we did, we kind of automated one of the patterns we found in this paper. This was our observation in the previous paper. What we observed was structurally similar methods inside a same class hierarchy are more likely to generate structurally similar test cases. So when I say structurally similar method, what does it mean? We can see for these two methods, they look alike. And if we generate some tree-level hierarchy like abstract syntax tree or XML, their tree structure will be same, but they will only vary in value level. Like we can see from the arrows, instead of duration field type, we have here period type. Instead of get field type, we have here get period type. And we can also observe from their test cases, they only vary in value level. We also proved it by applying it to 5 open source applications. For 24% of structurally similar methods for application 1, we were able to find 100% of test cases, those were structurally similar. And we can see like from 50% to 100% of test cases were structurally similar against like these 42%, 5%, and 20% structurally similar methods inside the source code. So motivated by this example and these statistics, we developed a test source evolver in this work to help generate test cases for structurally similar methods inside a class. Here we can see the basic overview of our approach. We have source code version 1, source code version 2, test code version 1. What we are trying to do is to generate test code for version 2. So first we are running some structural analysis based on the artifacts we have. We are parsing the source code and converting them to XML using one open source tool, source XML, so that we can manipulate the source code easily. And then we use another open source tool, Tran, to generate the XML schema definition XSD files from the XML. Why do we need this? As we have already said that we are looking for some group of methods, they are structurally similar, and the structurally similar methods only vary in value level. So if we generate XML schema definition file for structurally similar methods, the definition file will be same. So inside one class, we will have multiple groups where we will have structurally similar methods. And once we have group of structurally similar methods, what we do, we are generating test cases for the methods where the test cases are missed. I'm going to show them in subsequent slides. Like this is the example we have already discussed. There are two methods. They vary in some value levels. They are test methods, also vary in value level. For the first method, this is the hierarchical tree. And for the second method, we can see only here, these values are varying. So the basic structure is same. So what we are doing here, we are taking one test case as a prototype. And what we are doing, like in this example, if this is the method we are using as prototype, what we are doing, we are generating the list of differences. Like here, instead of this field is used. And in the corresponding test cases, we are also replacing these values and generating test cases for the newer method or for the method where the test case is missing. So this is how we evaluated TSC based on 4 research questions. First 2 research questions show the validity of TSC, and the third and fourth research questions show the usability of TSC. The first question is, how similar are TSC generated test cases based on the structurally similar method pattern compared to the test cases that are written by actual developers? And the second question was how we compare TSC to a state-of-art tool, EvoSuite. And our third question shows how common the occurrence of patterns generated by TSC. And the fourth research question was, how useful are the test cases generated by TSC with respect to the developer's effort reduction? These are the subject applications where we applied our research questions. So our first research question was how similar TSC generated test cases are compared to the test cases that are written by actual developers. So in order to evaluate what we have done, we took the methods that actually originally have test cases. Like for a group of methods, if there are more than one methods where test case exists, we took that group of methods because we will take one of the test case as our template and we will generate the remaining test cases to compare TSC generated test cases. So what we did, we used a state-of-the-art tool, contd, a pre-trained neural network model to do this evaluation. Like what contd does is treating the source code as a source code and generating some fixed length embedded vector. And so if we have 2 test cases, one generated by TSC and one generated by the developers, we are generating the embedded vectors. And then we are comparing those 2 vectors using cosine similarity. So if 2 vectors are closer to a space, then the cosine similarity is more similar. So in this case, if the cosine similarity is closer to 1, the result is good. This is one of the examples TSC generated. And we can see this is the existing test cases written by the developers, and this is the generated test case, and their cosine similarity value is 1. So one thing is here that contd considers both structural and semantic properties of the source code. That's why, although the names are different here, it's showing similarity value of 1. So this is a very good example of TSC generated test case. This is another example of test case with cosine similarity value of 0.804. And we can see here, actually, they look alike, but instead of assert false here, assert true was generated by TSC since the template it used assert true. And instead of assert true here, we have assert false. So the similarity value is not 1 here, but is 0.804. still the developer's effort is reduced. Like they have the basic prototype and they have to change this assert true to false and this assert false to true. So this is our result on 5 subject applications, and we can see all the box plot values here, like similarity, minimum value we found, similarity median, similarity max value, first quartile and third quartile, and then the similarity average percentage. Like here we can see from 70% to 100% similarity was found. And like in this application 3, the maximum amount of test cases was generated, and among all those 178 test cases, all of them had similarity value of 1, which is really motivating. And we can see the value is actually good in all other applications. And this is how we evaluated TSC to a state-of-the-art tool, EvoSuite. EvoSuite is a state-of-art automated test generation tool, and we did coverage analysis. We generated test cases for our subject applications using TSC and also using EvoSuite and compared the coverage. And this is what we found. To make to some sort of fair comparison, what we did, we only generated the test cases for methods those are structurally similar. And for one application, we were not able to generate test cases using EvoSuite, so there is no statistics for that one. But for the remaining one, we can see among all the test cases, the TSC generated test cases were 13 for structurally similar methods, and for EvoSuite it was 1. Like generated test cases ratio was 7.6%, and it was 0% for 2 applications, and for 1 application it was 50%. Our third research question was, how common is the occurrence of the structurally similar method co-evaluation pattern in software applications? Leveraging this pattern, to what extent TSC helps to generate new test cases? And here we can see the evaluation of our research question 3. We can see the total number of groups of structurally similar methods here. And here we can see the average size of structurally similar methods inside each group. And we can see here we have like 9 groups of methods that has at least 1 test case, and 9 groups of methods that has more than 1 test case. So if we generate some test cases based on existing one, we will be able to evaluate it. Like they have ground truth, and TSC generated like 13 test cases for 9 of those groups. So TSC generated more than minimum required test cases, and we are seeing the percentage for each subject applications. And this is how we evaluated our research question 4. We tried to kind of evaluate, is TSC generated test case reducing developers' effort? So we use token-based edit distance. So what we did, like if 2 methods, the generated one by TSC and the generated one by the developers, vary only by 1 token, the token distance is 1. So lower the distance, the better the results. So this is how we evaluated. So this column is showing like the minimum distance, like minimum distance we found was 1. Actually, for different method names, different test case names, it was also showing us difference 1. Actually, those 2 methods were similar. So this is kind of motivating that the minimum distance is so low, and we are having like good result. The lower the value of the percentage, the result is better. And so here for application 1, the result was not convincing, but for other applications we found good result. And here, once again, this one distance was because of naming difference. And so we can see that, so generated test cases by TSC, the developer will change only few tokens, which is really motivating. So this is all about our evaluation. And now I will discuss some limitations. Like one of the major limitations is like we are transferring the existing oracle, like we are taking one template and we are not replacing the expected value in the assertion statements. We are just transferring the current oracle. That is one of the problem or limitation we have to overcome, but still the developer can use the existing template and only rewrite those expected value if required. And another limitation is that we cannot ensure the generalizability of our approach, like if it's applicable to all other languages and all other platforms. So in conclusion, we developed and evaluated a prototype tool, TestSource Evolver, that automatically generate test cases for the newer version of a software. And our results show that TSC was able to generate 72% of test cases, which were associated with 38% of the source code with 89% similarity to the actual test cases written by the developers. Let me know if you have any questions.